Swayam Prabha. Digital India. Educated India.
Advanced OpenMP. So hope you have gotten a glimpse of OpenMP yesterday. So, and following this, we will also see hands-on.
Hello. Thank you, Preeti. Good morning, everyone. I hope I am audible. So, I was there for part of Sandeep's session yesterday. I think it was good. So, what we'll do today is we'll continue, as Preeti said, we'll continue from where Sandeep left off yesterday, right? And if you have any questions, please feel free to interrupt. The high-level plan is that we'll try and cover, so you know now the basics of OpenMP. How do you use work sharing constructs, some of the synchronization constructs, master, single, all this stuff, right? Locks. So what we'll discuss today is another concept in OpenMP, which is called tasks, right? Tasks, not threads. And then we'll talk about SIMD or vectorization. SIMD stands for single instruction, multiple data, right? And then, depending on time, we'll talk about memory models. Memory models, we'll briefly discuss memory models in general, right? So that you have some background if you don't already know it. And then we'll talk about memory models in the context of OpenMP, right? Because that is what we are studying, right? So OpenMP is a shared memory model abstraction, API, right? Any questions? So we'll begin with a few questions that I have for you, right? So take a look at this code. I have tried to increase the font as much as I could so that I could fit it on this slide. You can ignore all these int main, void and all that stuff, right? Assume that this code compiles. Try and run through it, and can you tell me what would be the outputs? This is just to get started. What would be the output? So anyone who volunteers, please say out your name, and then you can say what would be the output. I will read it for you in case it's not very visible at the back. So we start by cout. This is serial code, right? So this is a single, or there's only one thread now, the master thread. The parallel region hasn't yet started. Then we have a hash pragma OMP parallel. So now the parallel region has started. So this is a parallel construct, right? So that means this region we should have how many threads? Yes, how many threads will be there? Sorry, louder? Okay, so if I don't have any environment, okay, so that was the correct answer. One is option is what I set by the environment variable, right? So suppose my environment variable is not defined. So then what would be the answer over here? This region, how many threads? Number of cores in the system, that is usually the default, right? So if this is an 8-core system, then there would be 8 threads over here, clear? So that means how many threads will print this out? 8 threads, right? Again, the parallel region is done. So this is fork joint style parallelism. You fork a bunch of worker threads, they execute in parallel, then they join. Now again it will be serial code, right? So this part is serial code. Then I set OMP set num threads is 4. Suppose this is an 8-core machine, right? Then I start a second parallel region. How many threads will be here? 4. So this trumps the default that you have on the system, right? So even if you set the OMP set whatever, the variable name, environment variable name, that would be trumped by this function call, right? If you remember the slides from yesterday. So there would be 4 threads over here. Now I have another parallel region, hash pragma OMP parallel num threads, 12. So this is like the highest in priority. So for this parallel region, we would have 12 threads. Is that fine? Right? Pretty simple. And now what we have over here is cout OMP get nested. OMP underscore get underscore nested. Can anyone tell me what is this? Nested parallelism, right? So what is nested parallelism? Okay, yes, right. So you have threads, right? And each thread can launch a bunch of threads, right? See, this is kind of a nesting. So this is turned off by default, right? So in most compilers, Again, I'm just talking about, this more popular GCC, LLVM, Clang type compilers. For most compilers, this is turned off by default. So this would be 0. Why is it turned off by default? Anyone else? Yes, someone from this side? Why is nested parallelism turned off by default? Is it not a good thing, to recursively launch a bunch of threads? So I have 4 threads. Each of them will again launch a parallel region, and then you can go, like a chain reaction sort of a thing. This is turned off by default. Why? Any guesses? No, make a guess. Anyone? Yes? Segmentation fault is not the issue. The issue is that, well, at some point, beyond a certain number of threads, it doesn't benefit a lot, launching an arbitrary large number of threads. So if you have an 8-core system, launching like, say, 1024 threads will possibly not be of great benefit to you, right? Usually, unless all of those threads are kind of blocking, right? Usually what we launch of is like, if there are n number of cores, then we launch usually n number of threads, 1:1, right? So this is also called oversubscription. So oversubscription is not good. Similarly, undersubscription is not good. So therefore, this is turned off by default. So now we set nested to true. So now I am enabling nested parallelism, right? Now I set OMP set number of threads to 2. So what would be the print over here? I didn't print other stuff so that it fits on this slide. What would be the print over here? What would be the IDs? Anyone? Sorry? 4 threads? Okay. A bit more specific. Anyone else? 16? Why? So there are 2 threads over here. So 2 threads will start this region. They will hit here. So each thread will launch a nested parallel region. So that will again be of size 2. So 2 threads, 2 outer threads, 2 inner threads, right? So the IDs that will get printed over here is not 0 to 3, because they are 2 parallel regions. So the IDs would be 0, 1, 0, 1, right? The individual threads would be different. So don't mix up with the IDs. Fine. Any questions so far? Good. So another question. So we talked about work sharing construct in OpenMP yesterday, right? You have a for loop, or you have a iteration, and then you can distribute it amongst multiple threads. Hash pragma OMP parallel for. This is one way in which we can also try and distribute work, right? This is called cyclic distribution of work. Is this example clear to everyone? Yes, no? Doesn't matter. Third choice. Is this example clear to everyone? Fine. So here what we are doing is we have a pragma parallel region, and then we launch a bunch of threads over here. Based on my ID, I will access elements based on my ID, right? So if I am thread 0, so I will access, and there are n threads, so I will access element 0, n, n plus n, or whatever, right? If I am thread ID 1, then I will access element 1, n plus 1, 2n plus 1, so on and so forth. So it's like cyclic distribution of work, right? Then obviously the alternate is block distribution of work. So if you have an array of size n, you have say 4 threads, you could divide each into blocks of n by 4, and each thread can work on its own portion, right? Or chunking, right? Now the question is, if I have a computation like this, which one would you prefer? A block distribution or cyclic distribution? A block distribution, why? Sorry, louder? Spatial locality? Okay, fine. So you would prefer block distribution, right? Because if a thread accesses A0, you would want that thread to better access A1 instead of another thread, because then you will have better locality, right? Can you think of a situation where you might want to go for cyclic distribution? No? Sequential access of data. Why would you want that? Because that would still harm data locality. Can you be a bit more specific? If you have a linked list, can you iterate with a hash pragma OMP for? No, just think about it. If you have a linked list, can we use a hash pragma? Say I am iterating over a linked list, right? While my list is not null, next pointer is not null, right? And say there is no data dependence. All are independent operations. So can I use a hash pragma OMP parallel for in this case? Yes, no? Yes? Anyone who thinks yes? Why? No, that is fine. But there's still a challenge, right? You are talking about transformations, but without transformations we cannot use that, because then the loop count is kind of unknown, right? The compiler is not able to perform scheduling and all if your loop count is not known at runtime, right? So one option or one case where you might want to prefer cyclic distribution is to have load balance. Load balance, you might want cyclic distribution, because maybe working on one part of the chunk might take more time, or it might be more expensive, right? Suppose you are processing a graph, a Twitter graph, or a social network graph, where some nodes are very high degrees, some nodes have almost 0 degrees, right? Or like maybe degree 1. So another question. We'll get started, don't worry. I'm trying to get you guys involved. So here I have a no wait clause, right? So we have this is a work sharing construct, hash pragma OMP for. Suppose there is already a parallel region. This is a work sharing construct. So usually what happens is there is a barrier at the end, right? An implicit barrier at the end. So this is where all the threads after finishing will kind of come and wait for their friends to come, right? And only then they will proceed, the master thread will proceed. Fine. So if I have a no wait, what does it mean? Anyone? Threads don't wait, right? So they will skip past it as long as they are within the parallel region construct. So what can happen is if you have a second loop, then they can go proceed past and work on the second loop. So this is fine, right? Yes. Not really. Say this is part of a parallel region, right? There is an enclosing parallel block, and say there are 4 threads. No, suppose this is also part of the parallel region. This is not exactly a hash pragma OMP parallel for, right? Say I have split it. I have a hash pragma OMP parallel. I have the construct, right? Curly braces. And within it I have these 2 hash pragma OMP for, right? So that means this is a team of threads, that is the scope of the team of the threads. In the first region, there would be, say, 4 threads that are processing it. They finish, they will not wait for each other, and they will proceed past, and then they will, maybe start working on the second. Right? Make sense? This is this is for efficiency. So now I have this second piece of code. Will this work? A no wait? Anyone here? This is the same thing. I have a no wait. Will this work? Why? Sorry? Anyone? Louder? I'm short of hearing. Sorry? It's not independent. So the point over here is that there is a data dependence, right? For each A of I that I write over here, I am reading it. So there is a read to write dependence, or a true dependence, or a flow dependence, whatever you call it, right? So it is possible that if you are not careful, if you use a no wait over here, then A of 10 might not have been written here, and it might have been read later, because say a thread proceeded past it, right? So you may violate a data dependence. So you need to be careful in cases like this, right? So OpenMP is easy. In fact, one of the goals of developing OpenMP was to make non-CS experts back in the 90s or early 2000s, to make it easy for non-CS experts to, incrementally parallelize their code. So OpenMP is supposedly easy. It's made to be, or it's designed to be easy, but you have to be careful about certain cases, right? Just cannot be blind. Cannot just blindly add a hash pragma OMP parallel for and then think you are done, right? So you have to be careful about tricky situations like this. Any questions so far? Yes.
Suppose if the first for the thread 1 is executing I0 to 0 and I0 to 1.
Okay.
The same thread in the next call will execute I0 to 1 and 2 or some other array.
That is something that you can control, right? So that is something that you can control. Usually if you have static schedule as the default, then it will be the same chunking that happens. So if thread 0 used or operated on element 0 to say n, then it would be the same chunking in the second for loop as well.
The first follow, then again it's executing the
Yeah, it may not be same if you are using dynamic or some other scheduling clause, right? So I have not shown everything over here. It may not be the same if you are using dynamic schedule or something other, say a guided schedule, right? But that was a good question. Other questions? Fine.
Sir, I have a question.
Okay, yes.
Let's say we're doing social media profile for nodes which have high centrality or more outbound degree, sh- what should we make use of cyclic or like block?
Usually for cases like this, we go for cyclic, you know. So
Can I know why?
sorry?
Can I know why do we prefer cyclic?
We prefer it mostly for load balancing purposes. We prefer it mostly for load balancing purposes.
Thank you.
So maybe I'll skip over this. Oh, this is the last example. So one last question. So say this is again a sample code that I have. So do you see any problems with this code, or do you think this code is fine? So I have 3 variables, n, a vector, and a, and I have this work sharing construct, hash pragma OMP parallel for. I should be declared private. The index of the of the loop, which is just nested within the work sharing construct, is private by default. So I will be private by default. But that was a good try. Any other thoughts? So A is, sorry. So you are right. So I have over here specified default is none, right? That means the default sharing attribute is none. None of them are shared. So you have to explicitly specify the scope of each attribute, right? So this will actually lead to a compilation error because I have said n and vector are shared. I have not said anything about A. So if you try out this code, it will lead to a compilation error. Fine? Okay. So now we'll get started with tasks. So far, whatever you have discussed has been good, but it's been in the context of threads, thread-based programming, like say POSIX threads or whatever, Java threads, right? What we'll discuss now is tasks where we are talking about breaking down a programming, your programming logic into higher level abstractions which are not threads but tasks. So this is more like you can think of as task-based programming instead of thread-based programming, right? So the point is that not all programs have simple loops that OpenMP can parallelize, as we said. Like if you have a linked list, if you're iterating over a linked list, it's not so easy to parallelize, right? Then if you have bounds which are not known at runtime, that is difficult to parallelize, right? So then what do you do for cases like this? So this is a question that was already, this is a point that was already brought up. So I want to parallelize, say, this piece of code where this do work method is kind of, there's no dependence. Maybe I'm just doing some local computation, I'm printing out something. So I am sort of iterating over a linked list, and then I'm processing each data that is present in each node, right? Make sense? But if you use a hash pragma OMP parallel for, this is not going to work, right? So can you propose a solution to get around this problem with whatever knowledge that you have? Is there a way by which we could transform this code? Maybe someone else? Is there a way by which we can transform this code so that I can use hash pragma OMP parallel for parallelizing this task? Any thoughts? Is the question clear? I have a linked list, I'm iterating over it. What I'm claiming is it's difficult to directly apply hash pragma OMP parallel for or any work sharing construct. Can I transform this code so that I'm now able to use it? Changing while to for? Okay. What would be the steps? How the parameter P is getting changed. Okay. Maybe a bit more precise. So basically what we are doing, okay, yeah, go ahead. Okay, you're saying you add a if clause or something? Okay. The P next is not null or something? But then the loop count is not known at runtime, right? So I think what some of you are trying to get at is, what you could do is, first of all, you need to find out what is the loop count, right? So you do a pass, there might be other solutions, this is one possible solution. You do a pass, find out how many nodes there are. So then you get the bounds for your for loop, right? Now each of them is operating on a pointer, on an address, right? So what you can do is, you can fit all of those addresses maybe in an array. Again, there can be other ways. This is one way. Create an array of that size, store all of those pointers in that array, right? So now what you have is, you have an array, you know the count. Now you could use a hash pragma OMP parallel for, or basically a work sharing construct, right? So this is what we can do. So one option is, you iterate and count, create an array, right, a temporary array, and then you just have this hash pragma OMP whatever. This schedule is, you can add it, you may remove it, whatever, right? This works, right? Possibly this is what many of you had in mind. Are there any problems with this? Not efficient? What is the first step? Okay, so that is fine, yes. So this is definitely not efficient, and this is definitely not space efficient as well, right? Because I am having to iterate multiple times over the linked list, as some of you guys are pointing out, and then I also need this additional storage that I am having to introduce, right? So in short, this works, but this is a lot of work, right? So this is inelegant. So these are situations where you can use the task concept in OpenMP to try and get around this, writing this complicated code or complicated logic. So tasks were actually introduced in later versions of OpenMP. The current specification is 5.0. In later versions of OpenMP was when tasks got introduced. So basically, what tasks are is an independent logical unit of work, right? So say you guys are you possibly have written a lot of code with recursion. Think of this simple example. Think of you're trying to compute a Fibonacci series, right? Fibonacci of say n, right? So you can do it by recursion, right? Return Fibonacci of n minus 1 plus n minus 2 and whatever, right? So think of these each recursive calls. So if this was a sequential C program, what would happen is, you would have your stack, right? You call Fibonacci n, and then you do whatever local computation. You check if n is 0 or whatever you do, right? Logic. And then you go to, you push f Fibonacci of n minus 1. And then you finish that, recursion call, right? And then you go to Fibonacci of n minus 2. You finish that, right? You have a stack, that is what you maintain. So this is fine, but this is all sequential, right? Conceptually, Fibonacci of n minus 1 does not depend on Fibonacci of n minus 2, at least for this problem, right? So what I could do is, I could have one of my friends work on Fibonacci n minus 1, because these can be expensive operations for large numbers, for large values of n. These can be expensive, they can be time consuming. So I can ask one of my friends is, go ahead and compute Fibonacci n minus 1 for me. The second friend can go ahead and compute Fibonacci n minus 2 for me. They come back after some time, maybe 5 minutes, 10 minutes. They give me the result, and then I add, and then I forward it. So these are individual logical units of work or task, right? So that is how a task differs from a thread. By thread, we usually mean a unit of control, right? By task, we are saying it's a logical unit of work. So what would your task need? A task would need some code to execute, whatever data you want to compute on, and then some control variables, right? So threads are assigned to perform the work of each task. So in this case, in this Fibonacci example, what I can do is, I can have a parallel region of say 4 threads, right? And then depending on Fibonacci of n, what is the value of n, I can create individual units of work, right? I can create individual units of work, and then say these are the tasks. So I then add those tasks in a work queue, right? I maintain a queue of tasks that need to be performed. I add them to a work queue, and then these 4 threads, they are the worker threads. They will pick each a task from the work queue, they will compute it, and they will provide you the result, right? So that is kind of the relation. Is that clear? Any questions? So you have a queue of tasks that needs to be worked on. You have some number of threads. Number of threads can be a lot less than number of tasks. The very reason is that if you have an 8-core system, you may not want to launch 1024 threads, but it is fine to launch 1024 tasks. You see the difference? Because the number of worker threads is still 4. They will process those tasks based on their, their own scheduling method, when they have time and whatnot, right? So threads are assigned to perform the work of each task, and the runtime system, here I mean the OpenMP runtime system, right? The runtime system decides when tasks are executed. So I create a bunch of tasks, they are assigned in, or they are, they are added to the queue, And then it is upon the runtime system to decide when each thread will pick up a task and then execute it. Right? There's more to it, and we will try and discuss slowly as we go, but you get the idea. What do you mean? Of tasks? So Fibonacci is one example. We'll have a few more. Just hold on for a few. Okay. See, divide and conquer means here there are a lot of subtle differences, right? One difference is in divide and conquer, you actually progressively have simpler tasks to work with, or not tasks, simpler logical units of work, smaller units of work. That is not strictly the case, or that is not necessarily the case with tasks. Tasks can be, the same amount of work that you do repeatedly for, say, 10 times. So that is how it is different from divide and conquer. The paradigm is slightly different. You are trying to break up a complex work into smaller, progressively smaller units of work and then execute it. Yes?
So does a task have to be like the smallest logical unit of work that's possible?
It doesn't have to be. It depends on you. So you are the programmer. You can specify a task at any level. You can say Fibonacci of n-1 plus n-2 is a task, right? So that's up to you. It's a task. So task-based programming is a thing actually. In current. So how do you write parallel software nowadays? You could use thread-based parallelism. You could use You could use p-threads, right? But thread-based parallelism is considered to be a low level of abstraction because you are responsible for trying to create threads, trying to give them work, manage the work, manage load balancing, as our friend was talking about in case of social network graphs, manage load balancing, then manage when threads join, and then make them terminate. So everything depends on you. So you are responsible for the whole thing. But with task-based programming, you leave it to the runtime system. You say, I have to do this piece of work, this number of, these are the number of n logical units of work. You do it how you want. I don't care. Just give me the final result. So task-based programming is actually a higher abstraction of programming. And there are actually many languages, many libraries which support task-based programming. A very popular one is called Intel TBB, threading building blocks. In threading building blocks also you can, use these concepts of tasks. You create tasks and then there will be threads and it will be the runtime system which will ensure how to, schedule threads so that all these tasks can be executed efficiently. You don't have to bother with it. Although you have some amount of control. Okay, so let's continue. So this is exactly what we were discussing, right? So you have one master thread which will create tasks and then there will be these worker threads which will execute them but may not be immediately. It depends on the runtime system and it depends on you, right? Or if there are any dependencies that you specify between tasks, like task A has to complete before task B, right? So those things are possible. Yes? Yeah, so, right. So that is a good question. So the user has to find a logical unit of work that can be parallelized, right? So, and then you specify that, you package it up into a task and you launch a task. Yes. So this is your responsibility, yes. Yes?
Is there any case in which thread-based parallelism would be better than task-based parallelism?
Yeah, there could be cases where it depends on the kind of application that you are processing, right? So task-based parallelism always also has some overhead from the runtime because now the runtime is trying to having to deal with this. So cases where you have complete knowledge about what is the workload characteristic and all. In such cases, you might, or if things are very balanced, in cases there might be cases where you prefer thread-based parallelism. See, these are things that you cannot specify from, you cannot generalize. It depends on what domain you are working on, what application you are working on, the characteristic of the application. So let us continue. If there are more questions, I will take it in a couple of minutes. So the task construct includes a structured block of code. Inside a parallel region, a thread encountering a task construct will create a task, will launch a task, right? It will package up the code block and its data for execution. So basically, this is what we have. If you have serial tasks, you can package all of them and then run them parallelly with OpenMP, right? So hopefully, your end-to-end time will take will be less. And a task can be nested. So it's kind of, a task itself can generate a bunch of tasks. So this is one simple example, kind of contrived example. So what we have is, we have a parallel region, right? And then we have hash pragma OMP master. So basically what we are saying is, there is one thread which has the job of packaging up the work and launching tasks, right? So this is what you had in mind. So thread 0 packages the data because the master thread always has ID 0. And then it creates a bunch of tasks where say Fred, Daisy, Billy, these are independent functions, independent logical units of work, and they can proceed in some order. So there would be some n number of threads in this parallel region. So these tasks will be executed by those threads in some order, not necessarily sequential, right? So there's no guarantee that Fred will complete before Billy completes. You see the point, right? And at this point, all tasks will complete before this barrier ends. So we have a barrier over here, implicit barrier. So all tasks will complete before this barrier ends. Otherwise, we'll kind of block. So now there could be situations where you want to introduce some dependencies, that I want task A to complete before I start task B, or other possible cases. So like you studied synchronization constructs yesterday, right? So you also have some solutions in the context of tasks. So one obvious case is you can use a hash pragma OMP barrier, right? The other is you can say hash pragma OMP task wait. So basically what you are saying over here is that you wait for all your child tasks to complete. Before that you will not proceed, right? It applies only to children, not descendants. That means it does not apply to nested tasks. So here is another example. So we have a hash pragma OMP parallel region, right? And then I'm having a hash pragma OMP single. That means there is only one thread that will execute this block, right? How is a single different from master? Hash pragma OMP master, hash pragma OMP single. How are they different? Sorry? Not really. That is ordered. That is a different clause. Hash pragma OMP master. Do you know this? That means the master thread will execute. Hash pragma OMP single. Any thread can execute, not the master, need not be the master, right? So here only one thread will execute and it will launch tasks, right? It will print something, it will launch tasks. So what do you think would be the output in this first case? The one on the left hand side. What would be the output? Yes, anyone? A race is fun to watch. And what will happen with car? Will it crash? Go ahead. Yes. It's not necessary that only one of the two tasks can execute, right? We are not using any other dependency over here. Any other answers? Yes? Okay, right. So the point over here is that A will be printed because that is sequential, right? I launch a bunch of tasks, right? This task can execute in any order. So it's not necessary that race will be printed before car. So it can be R race car or it can be R car race. Both can happen. It's non-deterministic. It depends on your system, it depends on the workload and stuff. Make sense? Right? And then is fun to watch. Is fun to watch is not part of a task. So again, this order of is fun to watch can also be non-deterministic. So in most general cases, if you try this out, what you might see is is fun to watch because that is not part of a task. Launching a task also takes time, right? Like launching a thread, it's not free. It doesn't come for free. There is a overhead associated with it. So a possible output, at least when I was trying it out, is like is fun to watch race car, or is fun to watch car race, right? Clear? What would happen in the next case? It's almost similar, I just added a task wait. So that means what would be the output? Anyone else? A race car is fun to watch or a car race is fun to watch. So that is a task wait, right? It will wait for all the tasks to complete. So fun to watch now will not get printed before. Simple, easy. So another question. So say I have this simple piece of code, right? So what will be the sequence of? So I have a parallel region and then number of threads is n, right? So I have a hash pragma OMP task and then the task body is function of A, func A. So how many tasks will get created over here? Only one, right? The point is that there are n number of threads. I'm not using a hash pragma OMP single or hash pragma OMP master. See the difference? So all of these threads will actually execute this hash pragma OMP task, right? So there will be n tasks over here, right? And then you have a hash pragma OMP barrier. That means all of them will wait. They will finish. They will wait, right? And then now we have a single region. So func B will be executed. So that is only one task, right? So now the point is, how do we use tasks to deal with these complicated cases like iterating over linked list and other non-array like data structures, right? Because that was the motivation that we started with. How can we use tasks to adapt to cases like this? Well, the answer is pretty easy. What you can do is you have a hash pragma OMP parallel, then you have a single region. Why? Because I am just using one thread to create all the tasks, right? I have a single region, then I iterate over the linked list, and for each of these function that you use, say process on the node data, you can make it a task, right? So this function call that you have, you make it a task. So then this becomes a task. So now you have n number of tasks that get launched depending on the length of the linked list, and then they will be in the task queue. You will have say some number of threads, 4, 8, 12, whatever, doesn't matter. It is the responsibility of those tasks to those threads to pick up tasks from the queue and then process them. Simple. So now using tasks makes your parallelization of data structures like or parallelizing code with non-array like data structures like linked list much easier. You could use it to work on binary search tree or binary tree like data structures as well, right? So how do you want to do a post-order traversal or a pre-order traversal on a binary search tree? Using tasks. So what do we usually do? We go to a node, we visit its left child, right child, and then the current node, depending on in which order you want to print it. Does this make sense to everyone? Yes, no? Binary tree, right? Left child, right child. So how do you use tasks to deal with that? Any thoughts? The same way, very easy. So visit a node, then if the next node left child is not parallel, launch a task on the left child, launch a task on the right child, and you are done. Obviously, you might also need to wait for those tasks to finish depending on what computation you do, right? Make sense? Any questions? Okay, so this is what we had. So now the point is, how are tasks scheduled? So basically I have created a bunch of work, but how will they get executed? This is also important, right, for efficiency purposes. So tasks are tied to the thread that first creates them, right? Tasks are tied to the thread that first executes them. This need not necessarily be the creator thread, because there is only one creator thread, right? The first thread that gets to pick up or gets to work on a task gets attached to that task. That means it is that thread's responsibility to execute or finish completion of this task, right? So only the thread a task is tied to can execute it. This is something that is important, right? And this is mostly for locality purposes and other, it simplifies a lot of things. A task can be suspended at task scheduling points, right? For example, see here we are not actually talking about threads. This is a task. A task creation and finish, task wait, barrier, task yield. These are cases where a task can get suspended. Then the thread can move on to work on a different task, right? So when a thread encounters a task scheduling point, right? When a thread encounters a task scheduling point, it may do one of the following. What are some of the ideas? Well, depending on at least one idea could be it can go and try and execute a different task, right? Very simple. So there are certain conditions. So one possibility is it can begin execution of a tied task bound to the current team, right? or it can resume any suspended task, any task that was already suspended. It can try and resume executing it, right? Then there is also a concept of an untied task, which we'll just briefly discuss. So it can try and begin execution of an untied task. It can try and begin or resume execution of a suspended untied task, right? These are almost symmetric. Clear? And if more than one of the above choices is available, it depends on the implementation, the compiler developers, the LLVM, the OpenMP runtime developers to implement some priority amongst these. So we said that the thread which executes a task first gets tied to it, right? You may not want that. If you don't want that, you have something called an untied clause. If you use that untied clause, then they won't be tied. So then what happens is, you can resume at task scheduling points, you can resume, like say, if you use, okay, let me give a concrete example. Say I have task 223. I have thread 2. So thread 2 was the first thread that executed task 223. So now, under normal scenario, thread 2 would get tied to a task 223. That means it's thread 2's responsibility to ensure that task 223 finishes. Make sense? Right? Now there can be an alternative where you say that, well, I will use the untied scheme. That means thread 2 may be the first one which executed task 223, but if task 223 then gets, say, descheduled, right? Later, any other thread can execute task 223. It's not tied to task thread 2. Make sense? Right? So when can this be good? This can be good because to provide better load balancing. Because these tasks can have different amounts of work to be done. They may wait for other complicated stuff, I/O, memory access and all. So this is great, right? Can you think of any challenges in this, in the untied case? How will the state be transferred? You mean from one thread to the other thread, right? That is a good point. Anything else? That is actually a good answer. The point is, you looked at this block distribution of work, cyclic distribution of work. How did we do it? How did we do it? We used the thread ID to distribute work. Remember the first couple of slides that we had, or yesterday also, right? We usually use the thread ID to distribute work, cyclic or block. Now the thread ID can actually change because I am using the untied clause, right? So there's no longer necessary that only the same thread will execute the task. So things can change. So therefore, if you're using the untied clause, you need to be careful about a few cases, right? So any thread private variable that you have and other stuff, they may not be easily portable, right? Then when you use locks. Okay, so this is an example that we had. So basically, what we are trying to show over here is, I have a large number, right? I have some data on which I want to work. What I do over here is, I have a single region. I'm creating a bunch of tasks, right? I'm creating a bunch of tasks, but I am saying they're all untied. That means when they resume, they can be processed by any other thread, not necessarily the same thread. So this is something that we have already discussed. This is an example that I have just to have a contrived example. Any questions? Transfer of state will not happen. Transfer of state, if your logic depends on thread local variables, then that will not happen automatically, obviously, right? If you say that, well, if my thread ID is even, then do something, that may not work out, because then thread 3 might pick up execution of that task. Yeah, so we are sort of just scratching the surface. Well, this is a disclaimer. Whatever we are covering now isn't the whole of tasks in OpenMP. There's a lot more to it, a lot of other clauses. So priority is one of them. So you can assign priorities to tasks. So obviously, with higher priorities, tasks with higher priority will be, there's higher chance that they will be executed first. So there are more clauses that you can use to control these. Sorry? Okay, so point is, if you have one thread that has acquired a lock, right, and then it gets swapped out, the task is getting executed by another thread, then you can rely on the fact that well, this thread has already acquired the lock because now it is a different thread that is executing the task, right? That is not transferred. That is up to you. If you want to synchronize, yes, you had a question for a long time. Can you speak up? Okay. So, that is actually a good question. Sections are kind of, they are more like, they are not task-based programming in some sense. So, you have threads, that thread will execute, like you have a parallel region, you create sections out of it, and they will be executed like kind of asymmetrically amongst threads, but there you have limited control in terms of the scheduling and all. With tasks, it's kind of a more, what do you call it? You can think of it as a more elaborate mechanism for providing similar guarantees. Tasks or tasking is more powerful in terms of compared to sections. So, another construct that we'll study is the task yield directive, right? So, what this specifies is that the current task be suspended in favor of some other task, right? We said there are some scheduling points. Say thread 2 is executing task 223. I might want to deschedule task 223 and then work on a different task, right? How do you want that? One option is you could use a task yield directive. What that will tell to the runtime is that, well, now you can throw out or swap out task 223 and make or work on a different task, right? So this can be useful in cases where you are trying to do a busy wait sort of a thing, right? You are trying to test whether a lock is available, for example. So you are testing whether this lock is available, right? If the lock is not available, then you try and yield. That means, well, if the lock is not available, then I will not try immediately because then I will be burning CPU cycles, right? I don't want to be inefficient. If the lock is not available, I will wait for some time, I will yield myself, let the CPU or let the thread do some other useful work, and then I will try again sometime later, right? Make sense? And as I was telling you, there are a lot of other clauses that are part of tasks in OpenMP, like you can use priority, you can have depends, or you can introduce, dependency among tasks that, well, task A and B has to finish first because task C depends on that, right? These are very natural ways of thinking. So there are a lot of other clauses that you can use to come up or, implement such situations. Fine? So I think this is the last slide on tasks. So let's move on to a topic called SIMD programming. Yes? Can we initialize more than one master? That is not possible. In a team of threads, there is only one master thread with ID 0.
What if it is the reason speed up is slowing down?
What is the reason?
If there is only one master, it gives all the tasks to all the threads. So threads are parallelized, but master is not parallelized.
So you are worried about that creation of tasks can take up or eat up a lot of time. Is that what you are worried about? Yes? So, well, it depends on what application you are working on, right? If your application, if you can create tasks in parallel, that is fine. But usually that does not happen because usually, there is one person who distributes tasks, kind of the supervisor. So, and distribution of tasks is also often not part of the parallel region. The part of the parallel region is usually when you are doing the compute on the the data that you have, maybe an array of numbers and other stuff. But if that is your concern, then there should be ways of doing it. Sorry? Not really. So next we'll talk about SIMD programming. What does SIMD stand for? Single instruction, multiple data, right? What is the concept of SIMD? How does it help? Is it implemented as part of our modern machines, your laptops and all? Do we use SIMD? GPUs? Okay. So what we do over here is, first of all, we'll talk about single program multiple data, right? SPMD. So here what we are talking about is a OpenMP parallel region, right? You have a single each thread will run the same program, right? Each thread is running the same program, but on different portions of the data, different pieces of data. And your selection of data can be based on whatever branching conditions that you have, thread ID and stuff, like cyclic distribution, block-based distribution. So in OpenMP, what we do is we perform work division in parallel loops. So we usually query the thread ID, we query how many threads there are, we do then chunking, and then we divide work, right? It's like single programming multiple data. That can be a paradigm that you can think of. This is not SIMD yet. This we are talking about SPMD, right? So now we'll talk about other levels of parallelism with the hardware. So what are some of the levels of parallelism with the hardware? One is, well, instruction level parallelism, right? For example, you can have micro-architectural techniques like pipelining, or out-of-order execution, or superscalar architecture, which provides you instruction level parallelism, right? You process or you issue more instructions per cycle, right? Then you have something called vector level parallelism. Vector level parallelism, what we are saying is you have a vector processing instructions where you don't actually operate on a scalar piece of data, you operate on vector data. So that means instead of having an operand add, which adds two scalar operands, add A, B, C, that means I am adding B and C and storing it into A. I could actually have a vector instruction, say VAdd, which will operate on two vectors, add two vectors and then store them into a third vector, right? So if my vector is of size 8, that means I am doing 8 operations in one single instruction, right? So that is kind of, you are kind of expecting a 8 times speed up, right? So that is the concept of vector operations, right? And then you also have thread level parallelism or SMT, which we will not talk about here. So we are talking about vectorization. Vectorization in the context of, first of all, we'll try and understand it in the context of architecture support, and then compiler support, and then what OpenMP gives us. So the process of transforming a scalar operation on single data elements at a time, right? Single instruction, single data, to an operation on multiple data elements at once can be thought of as vectorization or SIMD. Right? I'm trying to use these terms interchangeably. SIMD is usually used from a architecture context, and vectorization is usually used from a compiler or PL context, but at least for this talk, I will use them interchangeably. So loop vectorization transforms a program so that the same operation is performed on multiple data elements at the same time, right? So that means, say, if you have a loop which is operating on n elements of an array, if you are using vectorization, and say the vector width is 4, you could then just iterate n by 4 times, right? That means on every iteration you are operating on more data instead of, say, one single scalar piece of data. So this is what we are talking about. So say I have this piece of code that I want to execute. So I'm adding two vectors, two arrays, AI and BI. Like AI is a one index. So in scalar mode, what I would do is I would have just add one scalar operand or two scalar operands, right? But in vector mode, what I can do is I can add all of this stuff together at the same time. If my vector width is of size 8, then I can add AI to AI plus 7 to BI plus 7 and have the result stored in CI to CI plus 7 in one single instruction. Does that make sense? Right? So notice over here that these are instructions. So we'll talk about it in more detail. So difference is, this is also VAdd, vector add, this is also VAdd, but here we say S and D, here we say P and S or P and D. So we'll talk about what that means. Basically, this means scalar, this means packed, and this means single precision or double precision. D is for single precision, D is for double precision, S is for single precision, right? So then what support do we need from the hardware for this, right? Yesterday Mainak was talking about your register files. That determines the width of the register files. That depends whether it is a 32-bit architecture, 64-bit architecture and stuff, right? So you have a register file. You say these are of 32 bits. So I could add all of them, X1 and Y1, and store it in Z1. This is say your assembly code, right? If you want to implement this, you need to have this loop run for n times, right? Now I want to use vector architecture. I want to use vector instructions. What that would mean is, I would add, say, if the width is 4, I would operate on 4 elements. Y1 to Y4, X1 to X4, and store them in Z1 to Z4. What would that mean? Now I would need fatter registers, right? because I am operating on 4 data elements. So I need fatter registers. So I would need a different register file or a vector register file to support this. Simple, make sense? Right? So you actually do this in or implement this in architecture, you need some support from the hardware. Right? You need fatter registers. Sorry? That is not, because now things are already in the registers. So you are actually operating on registers at this point, right? For memory operations, then the things are slightly different. So the point is, this is a graph from Intel actually, So what they are showing is, for some application, they try to benchmark some application. For some application, if you have serial code, then this is the performance that you get. On the x-axis, they have a metric for performance. So higher is better. So on the y-axis. So y-axis is performance. So higher is better. That means if your graph goes up, that is better, right? So what they are saying is, they tried out 2 ideas. One is threading, multi-threading, like say p-threads, and one is just vectorization, right? So each of them is giving you some improvement, at least for this application that they tried out. Each idea is giving you some improvement, but the best improvement that you get is when you combine them together. So you have multi-threading like OpenMP, you also have vectorization. When you club them together, that is when you get this enormous performance boost, right? So that is what is Intel trying to motivate with this slide, is that, well, multi-threading is good, OpenMP is good, like the basic OpenMP core is good, but you should also try and exploit features that the hardware is providing you. And what features is your hardware providing you? SIMD is one of them, right? Fatter registers and vector instructions. So Intel actually supports, and AMD and ARM also does that. Here we'll talk about in the context of Intel architectures. So Intel actually supports a lot of SIMD extensions. So for example, you have SSE2, SSE3, these are different generations, right? SSE2, SSE3, SSE4, AVX 512, AVX2 and all. So these are different architectures or different generations of support for vectorization or SIMD. Yes, did you have a question? Can you speak a bit louder?
For vectorization, we need a different hardware architecture. We need to have parallel.
Not different. I mean support for that.
Support.
Right.
So in the previous graph you showed, were all those experiments performed on the same hardware?
Yes.
Even the vectorized one and the.
Yes.
So they are changing as per the broadband.
Are they changing? No, these are across generations. But for a vertical slice, it's like the same hardware. So basically what we are talking about is use of SIMD units can speed up the program, right? So for example, Intel SSE has support for 128-bit vector registers, 128-bit, not 32, not 64, right? Vector registers and functional units. So that means you can now actually, if you have this support, you can actually perform 4 32-bit single precision, like operation on 4 single precision floating point numbers, or say 2 double precision floating point numbers, and so on and so forth. So you can now see, right, that you can do more work in less amount of time. Basically, you are issuing less instructions. So this is what you can think of. So if it is 128-bit wide, you can fit 2 int64s, or maybe 4 int32s, and so on and so forth, right? It depends on the data type that you are operating on or you are interested in. So based on these generations, whether it is SSE, whether it is AVX or AVX 512, Intel provides you different registers, different set of registers. So if you guys are interested in assembly programming, or writing low-level code with intrinsics and on Intel architectures, these would be the registers that you would be interested in. For example, you might have heard of EBP or these registers, ESP, EAX, RAX, right? So vector registers are different, as we said. Vector registers would be XMM0, YMM0, ZMM0, right? For vector operations, you would not possibly use EAX or EBP and stuff. So XMM registers are 128 bits, older generations. YMM is 256 bits, and ZMM is 512 bits. So the lower portion of a ZMM is basically your XMM, or the lower portion of your ZMM, half of it is your YMM, right? So this is how they have designed it. And what are x86 vector operations? A few examples. So one could be vmove APS. vmove APS. V stands for vector, right? Move for move. What is AU? AU stands for whether it is an aligned access or an unaligned access. That means whether the data is aligned to some word boundary or whether it is unaligned. Nowadays, it doesn't really matter unaligned accesses. Things have improved a lot. In older days, unaligned accesses were often not allowed, or they lead to segmentation faults and stuff, performance difference. Okay, so AU stands for aligned or unaligned, right? P or S stands for whether it is packed or scalar. That means whether it is a vector operand or a scalar operand. Scalar operand means only one. And then D and S, the last one stands for whether it is double precision or single precision, right? So by looking at the instruction, you can find out what it is operating on, what type of data it is operating on. Okay, so we have it over here. So for example, if I have a move SS or a V move A PD, that means it is a vector move, aligned, packed, and double precision, right? Okay, so this can be one example that we look at. So say we do this V add SS. So I issue an instruction V add SS, vector add, scalar, and single precision. What this means is, what I'll do is, I'll have data in XMM2 register, 0 to 31, this is scalar, right? 0 to 31 bits. I will add XMM2, XMM1 to XMM0, right? Like your regular assembly programming that you do, right? If it was packed, then it would possibly have been like say 0 to 64, 0 to 63 or 0 to 127. So on recent machines, what this slide is trying to show is, this picture is slightly blurry it seems. On recent generations, support for vectorization has grown tremendously. Now Intel is actually investing a lot to extend capabilities of vectorization in their hardware. So the number of vector instructions that you have now has almost is like greater than 3,000. It's almost like, is increasing at a very steep rate. That is what we are trying to show in this slide. So basically what it means is, don't just rely on trying to, write a parallel program. If you want to write an efficient code, you should also try and make use of these other features that architects are providing you, and even languages like, standards like OpenMP also provide support for vectorization, and that is what we'll look at. So how do you vectorize code? So far what we have been discussing is vectorization from, or SIMD from an architecture point of view, right? That hardware gives you this support. Now the point is, we need to exploit it. So you see the flow, right? We talked about tasks. Now we are talking about SIMD or vectorization. We said hardware gives you this support. Now we need to exploit that support. How do you exploit that support? Well, you could write assembly programs, right? But we don't want to do it. So there are other choices. Other choices are, you can have vector intrinsics. So you can write C-like programs which has support for vectorization, or you can hope that the compiler will auto-vectorize your code. That means if you have a for loop like this, which we often, we often write code like this, you try to parallelize it with an OpenMP work sharing construct. One option is, you can hope that the compiler will translate this code to make use of these vector instructions. So instead of generating a single scalar add, it will probably issue a V move add P or whatever, instruction that is there on the target machine, right? So this is what you are hoping for, to get good performance. So the advantages are, obviously auto-vectorization is the most portable, because then you don't need to do anything. The compiler will do everything for you, right? So the compiler will vectorize automatically, you don't have code changes. Or what you can do is, you can also try and do it yourself with inline assembly or SIMD vector intrinsics, but then you have more control, but it is less portable. It is more work for you, less productive, right? Another option is, you can actually use SIMD capable libraries. So when you are writing programs, say you are doing basic linear algebra operations and stuff, you can use libraries like Intel Math kernel library, which already has support for vectorization. So these are things that you need to be aware of when you are serious about developing an efficient application, an efficient software, right? Make sense? So auto-vectorization, the good things are that it is transparent to the programmer. The compiler does it for you. Compilers can also apply other transformations, other optimizations. And it is also portable code across architectures, because you have the compiler as an intermediate, right? However, compilers may fail to vectorize. Compilers may fail to vectorize because, there is a limit to what a compiler can do. There's a limit, it may infer wrong things about your code, wrong false dependencies. So in those cases, you can help the compiler by providing hints, or you can force the compiler to actually vectorize it. If you as a programmer is sure that this code can be vectorized. So why would compilers fail or auto-vectorizers fail? Well, you could have data dependencies, you could have unaligned accesses, you could have function calls, you have complex control flow. These are cases which makes analysis, program analysis very difficult for the compiler. So the compiler doesn't want to make wrong decisions. It doesn't want to transform your code in a wrong way, in an incorrect way. So it will just throw its hand up and say, well, I'll be conservative, I'll not vectorize this code, right? So in such cases, what you can do is, you can actually add some hints to your code to help the compiler auto-vectorize it, right? So now we come to OpenMP. How does OpenMP help you with this, right? So in older versions of OpenMP, what you could do is, you could say, so you have this piece of code, AI, BI plus 10, right? I could try and vectorize it, right? Pretty simple. I would use this vmove add or whatever, sorry, vadd ps or vadd pd operations, instructions, right? Now I want the compiler to auto-vectorize this code for me. I don't want to write assembly, or I don't want to use intrinsics. So I could use this hints. I could use this hash pragmas, right? So I would say hash pragma OMP parallel for. That means it will use threads to it will do work sharing, right? But in addition, I want to do vectorization. So what I would do is, I would use hash pragma ivdep. Ivdep tells you that there aren't any dependencies in this. Believe me, basically this is a hint that you are giving to the compiler. There aren't any dependencies. Go ahead and vectorize it. And hash pragma vector always is another hint to the compiler to say that, well, don't rely on your efficiency heuristics. Trust me, go ahead and vectorize it, right? So this is one way with which in older versions of OpenMP you can introduce support for vectorization in your code, right? Now the problem with this is that these are vendor specific. Hash pragma ivdep. This is for Intel compilers. For the GNU GCC it is different, right? So that means these are not portable. So therefore for newer versions of OpenMP, newer specifications of OpenMP, they have tried to provide support or first class support for SIMD parallelization, right? So these are the constructs. So far you have looked at hash pragma OMP parallel, hash pragma OMP parallel for, hash pragma sections, what hash pragma tasks. This is hash pragma OMP SIMD, right? And the other one is hash pragma OMP declare SIMD. So we will talk about these. So I think let us go to the example first. No, maybe okay, fine. So hash pragma OMP SIMD, what it says is you have a for loop. You can say hash pragma OMP SIMD. That means this is a hint to say that go ahead and vectorize this for loop, right? Note that this does not parallelize the loop body. I am not saying hash pragma OMP parallel for or anything. I am just saying hash pragma OMP SIMD. That means go ahead, you are free to vectorize this for loop that I have, right? The other option is hash pragma OMP declare SIMD. So you can add it to a function definition. So when you add it to a function definition, what this will do is, this will generate different versions of that function. Some of them would have support for vectorization, right? The other option is, okay, this was I think the same. Hash pragma OMP declare SIMD, okay. This is the same, this is the function definition. So basically what we are doing over here is, we have a function definition, float of min and then float A, float B. Very simple function definition, right? If I say hash pragma OMP declare SIMD, what this will do is, then the compiler will generate different versions. Some of them would be for scalar data types. Some of them would be for vector data types as well, right? So assume for now that vector 8 is a vector data type, right? Where you can process say 8 operands at a time. So then there could be one version which says vector 8, vector 8, vector 8b. So that means you would compare 8 operands at a time. So just by adding this hash pragma OMP declare SIMD, you are automatically requesting the compiler to generate a vectorized version of your code, right? So you could expect a n by 8 times speed up. Well, that is the ideal case, but that is a good thing to have, right? N by 8 times speed up. The other option is hash pragma OMP for SIMD. This is different from hash pragma OMP SIMD. This has a for in between. In this case, it did not parallelize the body. It just said vectorize it. Now we are saying hash pragma OMP for SIMD. So what this will do is this will both parallelize it as well as use vectorization, right? So it will parallelize and vectorize the loop nest, and then the rest are similar. So basically you will have all this chunking thing that you have going on, and then you also subdivide the chunks to fit in a vector register. So say a thread gets some amount of work to do. Now within that amount of work, you will again subdivide the work so that you can do more as long as that fits in a vector register. Make sense?
This one refers to the retail side of 187 bits. What is it?
Hash pragma OMP for SMD? Yes, good. Thank you for pointing it out. So basically, what Ashish? Sorry. What Ashish is saying is that this plot that we said, where Intel was saying that use both vectorization as well as parallelism to get maximum benefits, is this, right? So you have parallelism as well as you have vectorization. Make sense? Questions? So here I have an example. This slightly, I've tried to remove all the craft, but this was the largest font size that I could fit. So I'll try and help you read it out if it is easy. So the point is, I have an array X, right? I have an array X and I'm trying to just sum it up. Well, you can try and parallelize it very easily with a work sharing construct, but we'll try and use SIMD over here. Is the problem clear? Right? So we have X of I. I can add it up sequentially, sequential sum, right? What I could do is I could also try and add it up with a hash pragma OMP SIMD. You see what I'm doing over here? This is not a hash pragma OMP parallel for. You are free to use it, but this is a SIMD construct. So that means depending on your vector width, you expect a speed up of, say, if it is vector width is of, say, 4 operands, you expect a speed up of n by 4. If this took a time of n, this would take n by 4, ideal case. Make sense? If the vector width is 8 operands, then speed up will be 8 by 8, right? That means your loop will iterate fewer times, n by 8 times, n by 4 times. And then over here, what I'm doing is I'm actually using hash pragma OMP parallel for SIMD. So I'm trying to use work sharing as well as SIMD support. So in this case, what is going to happen? Can anyone explain? What is going to happen in the last case? Okay, yes, now 4 threads. So right. So it will divide the work into 4 chunks, and then within each chunk it will use vectorization. Right? So you have 2 levels of parallelism. Right? So which one do you expect to be faster? The last one. Right? If you try it out, even on my laptop, it was about 2 point some times faster. Make sense? Fine. Any questions so far? Any questions? So OpenMP actually provides support for a lot of additional features that we won't be covering in this couple of days. For example, OpenMP also now provides support for programming on heterogeneous devices, right, and a lot of other things. OpenMP is like quite popular standard. So if you guys are interested, you guys can go ahead and learn more of it. This is just a brief brush up or like a brief touch up on OpenMP concepts. Fine. So the last topic that we'll discuss today is OpenMP memory model, right? So again, to start off with, we'll briefly discuss what do I mean by a memory model, and then we'll discuss memory model from OpenMP's perspective, right? But maybe memory model is a new concept to some of you. Has anyone of you heard about memory models, shared memory models, sequential consistency, TSO, PSO? Okay. So this may be a new topic. So therefore, we'll go slow. We'll discuss briefly the background of memory models, and then we'll talk about memory models in the context of OpenMP, right? Here is a simple Java style program. Okay. Shared memory program. So I have an object X, I have a boolean done false, and then I have 2 threads. Thread T1, thread T2. Thread T1 is initializing an object and then setting a flag to, it's like it's the producer thread, right? It's initializing an object, setting the flag to true. You have consumer threads like thread 2. It will wait till the flag is true and then it will go ahead and consume the data, right? We possibly have written code like this, like, at some point in our lives. So, what do you think? How many of you have written code like this? The others are smarter, they don't. So, how many of you haven't written code like this? Why? You use any synchronization constructs or something? Fine. So, do you think everything is fine with this piece of code? Any guesses? Do you think everything is fine with this piece of code? Race condition? Race condition on done. Okay, so do you know what is a race condition? This is actually a data race. So there is a subtle difference between a race condition and a data race. This is what I would call a data race, to be more technically correct. So a data race means that you have concurrent and conflicting accesses to a shared memory variable, right? That is the definition of a data race. You have concurrent and conflicting accesses to a shared memory variable. What I mean is, I have the variable done over here is a shared memory variable. You have conflicting accesses. That means at least one of the accesses is a write. One is a read, one is a write, right? And they are concurrent. They are not correctly synchronized, right? So this guy is writing it, this guy is reading it. So as your friend tried to point out, there is a data race on the shared variable done, right? Given that knowledge, can you see something going wrong in this? Try it. Try and say something, some answers. Can you see anything going wrong in this? Compilers, I'll give you a hint. Compilers perform optimizations, right? Compilers perform a lot of optimizations. Now, all these optimizations are from the context of a single thread. Compiler doesn't know how many threads you are going to launch for a C-like program or C++ program, Java program. So compilers perform optimizations from the context of a single thread, single-threaded context, right? So given that, can you think of any compiler optimizations that can break this piece of code? Well, this piece of code can break, right? Fine. There could be a lot of problems that can happen with this piece of code, right? Things like this can happen. So what can happen is, first of all, this is what your friend was saying, right? Done and X, there are two stores. These are two store operations, two write operations. They are not data dependent. A compiler is free to reorder them. Your hardware is free to reorder them. Right? Questions? We'll go slow. Questions? So if that happens, then this scenario can happen, right? The flag gets set to true first and then this happens, but what will happen will be, this will come out of this, and then you access x.compute and you get into you get a null pointer exception in the Java world. Right? Make sense? This is possible. The other is that this done variable, so compiler will try and optimize this piece of code. It will see that, well, I have a while loop, I have a variable done, but a done variable is never changed within the body, loop body, right? So I could perform some optimization called loop invariant code motion, LICM, loop invariant code motion, because the done is not getting changed at all, and it is a shared memory location. I need to fetch it from memory. What I can do is, I can fetch it from memory, I can put it into a register or into a local variable, because accesses to a register and the local variables are faster, right? So what it can do is, it can try and put done in something called temp, a register or a local variable, and then use temp over here, right? So then this becomes cached. So even if you set done to true, this thread will never come out of the infinite loop that it gets into. See the point? A more subtle error can be that this guy gets to see a partially stored object X, right? That is a more subtle error, because then you don't get a null pointer exception, you don't get an infinite loop. You will just see a wrong output. That is even more harder to catch. So these are some, some challenges with concurrent programming, right? So I have another question for you. So I have two cores now. Now think from a architect's point of view. I have two cores, C1 and C2. Each of them are performing some operations. So store 10 to X. This is a pseudocode, right? So just assume store 10 to X, store 1 to done, right? and this guy is performing these reads. So very similar to the example we had on the last slide. So you are trying to load done to register R1. You are trying to iterate over here, till R1 is not 1, kind of loop. And once this is done, then we load X to R2. This is exactly like what we had earlier, just that this is like, say, some sort of pseudo assembly code, right? My question is, what value can a read return? So what value do you get to expect over here? When you do load of X R2, what do you expect R2 to contain? Sorry, louder. You expect X to contain 10. Any other answers? Junk value. Well, say X is 0 initially. So can X be 0? Yes. For reasons similar to what we had on the last slide. X can be 0 as well, right? Because this can get swapped. There's no dependence. No one is preventing it from happening, right? So these are some challenges with shared memory programming, both at the compiler level as well as at the architecture level, right? When you write multi-threaded code. So these are things that you need to take care of. And this is important because in OpenMP you are actually learning about writing multi-threaded code, right? So what kind of reorderings can a hardware perform? It can perform store-store reorderings. You have two stores, they get reordered. It can perform store-load reordering, right? By reordering I mean they appear as if they have been reordered, the load happens first. It can perform obviously load-store and store-load reorderings. Simple? Any questions so far? Please ask. Any questions?
This is on this, on the reordering on this, running on the same code.
Same code but different addresses. Because if they are the same address, then you have data dependence. Obviously, if you have a read to an address and then a write to an address, the compiler should not reorder it unless it can ensure that it's like, there's no side effect, right? That is fine, but this is at a lower granularity. A mathematical expression will possibly contain a lot of, access a lot of memory locations and all. Here I'm talking about individual operations, memory operations. So all these reorderings are correct in a single threaded context. This I think is one of the, most important slides in what we'll discuss in the next few minutes. All of these reorderings are correct from a single threaded context. Because if you have only one thread, it doesn't really matter. It's as if nothing is, But the problem is this, it is non-trivial in a multi-threaded context. If you perform these reorderings, then it can actually impact the correctness of your program. And I hope I have been able to convince you with those two examples, right? The Java style example and the pseudocode style example, assembly language like example, right? So the point is that when you perform a load, what value are you expected to see? Like when we loaded X, we said, can we see 10 or can we see 0? What are we expecting to see, right? So usually what we think of intuitively is that whatever was the value of the last write, that is what we'll read. If I wrote 10 and 20 and then I read it, I expect to see 20. I don't expect to see 10, right? So this is very easy in a uniprocessor system, because in a uniprocessor system, there is only one thread of control. So you write 10, you write 20, you write 30, and then you read it, you expect to see 30, right? But the point is more challenging or more subtle in a multiprocessor system, because now you have so many things that are writing to. Say this is writing 10, this is writing 20, 30, 40. So if you read it, which one of these is last to you? Right? So the definition of last in this context is kind of more bloody. You see the point? Is this clear to everyone? Right? So the definition of last is kind of bloody. How do you define last? Is 30 last or is 40 last? So this is where a memory consistency model comes in handy, right? So a memory consistency model is a bunch of rules which tells you, in a layman's word, it tells you that if I perform a read on this system, what is the value that I am expected to see? If you are, say, running your experiment on an AMD system, you are writing 30, 40, 50, 60, whatever. If you read it, the memory consistency model of the AMD system will tell you what value you are expected to see. If it isn't that value, then your architecture implementation is buggy. You can complain to AMD, right? Similarly, now you have language memory models. So you have memory models at the architecture level or the hardware level, you have memory consistency models at the language level. C++, Java all have memory consistency models. So if you have a parallel program in Java and you have, you are writing x equal to 20, x equal to 30 and you read it, the Java consistency model tells you what value is that read supposed to return. Will it return 30 or will it return 40, right? So this is actually important because now you can try and reason about what interleavings you can have, right? It actually has an impact, or it actually has the most impact on the behavior of your multi-threaded program. Because see, writes are usually, they don't have, reads are usually considered to be more important because you can take branching decisions, or your control flow can change based on a read. Usually control flows don't change based on a write. They mostly change based on a read, because you will read something and then you will have a predicate and then you will either go in the true path or the false path and so on and so forth, right? So memory consistency models are important because it determines what optimizations are correct, right? It is a contract between the programmer and the hardware. So when you write a program, this is what the value that your hardware is supposed to give you. This is a kind of a guarantee, right? It influences the ease of programming and program performance, and it also impacts portability. That means if you write say 30 and 40 and say AMD tells you I will return 30 and Intel tells you I will return 40, then the code is not going to be portable, right? So this is Decker's algorithm. You guys might have studied it in some form in your operating systems class, right? Decker's algorithm for ensuring mutual exclusion. So this is like this pseudocode style that we have over here. So same, I have two flags, flag 1 and flag 2, both are set to 0, fine. Then I have core C1, I have core C2. I perform this store of flag 1 to 1, I store 1 to flag 1, I store 1 to flag 2, and then I am trying to load the values of the other flags. Basically, I am trying to see whose turn is it, right? Decker's algorithm. I am trying to see whose turn is it. Can both R1, question is, can both R1 and R2 be set to 0, right? I have store load. Can both R1 and R2 be set to 0? Yes, no? If yes, why? If no, why? Sorry? See, for this to be 0, both need to be, at least one of them will be 1 is the answer. Any other answers? Take a couple of minutes, please think, and then, otherwise it will get possibly a bit more difficult as we move along. See, if this executes first, then this, then flag 1 will be 1, right? Flag 2 can be 0. So if my execution order is S1, L1, S2, L2, then at least 1 will be 1, right? Similarly, if it is S2, L2, S1, L1, at least 1 will be 1. For both of them to be 0, what needs to happen? Both needs to get reordered. S1, L1, S2, L2. Can that happen? On our current Intel machines, that can happen, right? So basically, if you try and implement a naive Decker's algorithm for mutual exclusion of your code, you don't use pthread mutexes, you don't use Java style locks, you will say I will be cute, I will try and implement my own mutual exclusion algorithm, then your code is broken. Because on Intel machines, both can be 0 and then both threads can enter the critical section. You see the point? So next we'll talk about the simplest memory consistency model that you can think of. This is called sequential consistency. Okay? It's a mouthful, but the idea is very simple. So you have multiple threads of control, or you have multiple cores executing instructions, right? So these are 2 threads or 2 cores. What sequentially consistency tells you is that, okay, first of all, this is the order in which instructions are executing. So this is also called program order. This is also called program order, right? Like A equal to 1, B equal to 2, this is program order. So you have 2 threads or 2 cores executing instructions. Sequential consistency tells that the final interleaving that will happen, either this or whatever, right? They will interleave, right? This is multi-threaded execution. The final interleaving will happen as if all of them execute in program order. That means they won't get reordered. You see the point? So whatever is program order will be respected. They won't get reordered. That means with sequential consistency, these cannot be 0. So if you have an architecture or if you have a language that implements sequential consistency memory model, then this Decker's algorithm will work. Make sense? Because Decker, Peterson, they tried to come up with these algorithms back in the 60s, right? Then we didn't have this concept of multi-core or parallelism. So therefore, they were correct in their in their generation, right? So if we have sequential consistency, then S1 and L1 are not allowed to reorder. S2 and L2 are not allowed to reorder. They can interleave either S1, S2, L1, L2, or S1, L1, S2, L2, whatever. You see the point? So this is the simplest sequential consistency. Any questions? So this is the same example that we had, right? So core 1, core 2, I stored this to this, I stored this to this, and then I load, and based on, I keep on iterating as long as the variable flag is not set, and then I load data. So question is, should R2 always be set to new? That means, should I see new for this variable, right? If this is sequential consistency, then it is guaranteed to see new, right? Because these won't get reordered. Is the idea clear? Sequential consistency, no reorderings are allowed. You can just interleave. Questions? Sorry? They cannot reorder within individual cores as well. Okay? So even within individual cores, even within individual threads, they have to respect program order. And by respecting program order, you can interleave in any way. This, whatever. Right? So this is what we have. So you cannot reorder within your program, within your core, within your thread. Then you can interleave in any way. So this is like per thread program order, or per thread or per core, whatever you call it. And then this is like the global ordering. The middle one is the global ordering, right? Questions? So in sequential consistency, every load gets its value from the last write, because there is no reordering. Every load or read is getting its value from the last write. So which is what we understand. The point is, if you have two addresses A and B, these two addresses can be different, right? Because if they are the same address, then obviously you have to respect data dependence. These are different addresses. A may not be equal to B. Then if you have, in sequential consistency, the rules are like this. If you have a load of A that is coming before a load of B, then that cannot be reordered. If you have a store of A coming before store of B, that cannot be reordered. So all these four cases you see, nothing is getting reordered. So this is just a brief, simple formalism for sequential consistency. We said there could be 4 reorderings: store, load, store, and what did I miss out? Whatever the fourth one. So nothing can be reordered, right? So this is all fine, but then this actually can lead to a performance bottleneck. Because current hardware is a kind of out of order. Your compilers perform a lot of optimizations. They perform loop invariant code motion for all this, for dead store elimination, redundant load elimination, and all this stuff. With sequential consistency, many of these optimizations are not allowed, right? Because in SC, you are not allowed to perform any reorderings. It's very strict. So if you have an end-to-end SC system, an end-to-end sequential consistency system, like say you are writing OpenMP on a sequential consistency memory model, you run it on an architecture on a hardware that is sequentially consistent, then your program will probably run a few times slower. Whether it is 5%, 10%, 100% is something that I don't know, right? But it will run slower. Is the point clear? So therefore, current compilers, architectures, they are more aggressive. They are more aggressive. They want to perform a lot more optimizations. Therefore, SC is not the current standard memory model, right? So current memory models are usually TSO or PSO. So we have existing memory consistency models both at the hardware level, SC. There is something called total store order, which is basically the default on your Intel machines. If you have an Intel machine, then the memory model that you have is actually total store order. And you also have memory models for programming languages like Java, C++, and in fact, OpenMP also has one, so that is why we are discussing this. Any questions so far? So let us start. So what we'll do is we'll continue from where we left off, right? Try and finish or wrap up in maybe 10-15 minutes, because we have a few problems that we would like you guys to practice and try out. Otherwise, it won't be very meaningful. So far we have discussed task programming, or the abstraction of tasks in the context of OpenMP, right? More of a logical thing. Then we talked about SIMD support in OpenMP. Now we are trying to discuss the last piece, at least for this hour, where we talk about memory models. Now, to understand OpenMP memory models, we have been discussing memory models more generically, like what happens with memory models of existing architectures, programming languages. We looked at sequential consistency. We'll then talk about a couple from these list. You have memory models at the hardware level, sequential consistency, total store order, partial store order, weak ordering. You have memory models defined for languages and abstractions like OpenMP, Java, and C++. So, flow is clear? So, what we said that sequential consistency is kind of the basic memory model, right? The easiest, where program order is going to be respected. So, basically, program order from multiple cores, multiple threads will be respected. They can interleave in any order, that is fine, but they won't get reordered within a core or within a thread. Fine. Now, as I said, your current laptop possibly does not implement sequential consistency. So that means if you run your Decker's algorithm on your laptop, it can very well fail, right? May not fail in 10 runs, may not fail in 1,000,000 runs, but it can fail sometime. And this is important. Can fail thing is very important when you talk about developing safety critical applications. You cannot say that, well, it will run fine if I run it for 1,000,000 times, who cares? But if I run it for, what will happen if I run it for a first time after 1,000,000, right? That is what is important. So usually what the memory model that your current Intel machines support is widely conjectured to be this, total store order, right? Or often called TSO as an acronym. So what this says is it allows reordering stores to loads. This is the most important line for TSO. So in SC, no reorderings are allowed, right? But we said SC can be bad for performance because then compilers cannot perform a lot of optimizations. So what TSO allows you to do is, TSO allows a store and a load to get reordered. That means you have a store, you have a load, the load can get reordered to the store, right? TSO does not allow reordering stores, loads, and load stores. So out of those 4 possible combinations, only one is allowed to get reordered. Clear? So that means, okay, so we talked about this. So this is the same formalism that we looked at for SC, right? And I hope you can make out the difference, the one that has been struck off. In SC, nothing is allowed to be reordered, irrespective of whether it is the same address or a different address. You might say, well, if it is a different address, there is no dependence. That is how it is different from data dependence, right? If you have different addresses, even then you are not allowed to reorder. So this store to load reordering, that means a store happened, in the same core or load happened, they can get reordered in a TSO memory model. Fine? If they are the same memory address, then obviously there is a data dependence, that there is a different question altogether, that has to be respected, right? So you cannot violate any correctness that a programmer intends. So this actually enables an optimization called the first in, first out write buffer or a store buffer. So many people use store buffer, many people use write buffer. I often use them interchangeably, right? So so the reason is this. So say I have a program, right? I have a program, I have reads and writes. So which do you think is more common, reads or writes? Reads are more common, right? So from an architect's point of view, loads are more common, right? So what is the usual ratio? It's about maybe 60% to 40% or 70% to 30%. So that means 70% reads to 30% writes. It depends on the application, but usually that is the common case, right? So therefore, reads are more performance critical. You don't want your reads to get delayed. You see the point? It's like Amdahl's law, right? Because writes are only 20% or 30%. So you want to improve performance for the majority of the application which are reads, right? So you don't want to delay your reads. So what now think that a core is performing a store operation, right? Now think of a core that is performing a store operation. What needs to be done? To perform a store operation, you need to fetch that line containing the address from main memory to your own cache, if it is not already there. If it is not already there, right? In other cases, so that takes some time. Then you change the state of it. You usually have a cache coherence protocol. Current variants are Messi based. So you need to change the state to a modified state, right? That also requires acknowledgements or invalidations from other cores, depending on how many other cores have that line cached, right? And then you write it. If you write it, what do you need to do? That means in a naive implementation, that write or that store operation should trickle down to your cache and to your main memory, right? Agreed? Now this is not free, this takes time. This takes time because accesses to memory is expensive, right? And then because of this quorums protocol, you might also need to wait for invalidations. So that means, especially if you have a cache miss. So if you have a store followed by a load, then that load can get delayed because of this read or this write operation. That means, say I have already performed the computation, I am now trying to write it. If I want to write it, it will need to write it into my cache. So I need to wait for maybe I need to wait for a cache invalidation. I may need to wait for a invalidation message from a remote core, and then it will trickle down to memory. So while this is not actually fundamental to the execution of the program, I've already performed that computation, right? So the computation is already done, maybe store 10 or whatever. Now it just needs to get reflected into main memory. Why delay the load operation that is following it? You see the point? Otherwise the load operation that is following it will get delayed. And we said loads are more performance sensitive, right? So therefore this is the idea of having a store buffer. So what happens is, as long as this instruction completes, you put it into the store buffer and then you allow the load to get reordered. That means the store is not yet visible to main memory. It may not have been written back to main memory, but the load gets reordered and the load gets to execute. You are trying to improve efficiency of your program. You see the point? Right? So you are allowing load store load reordering. And all these stores will go into the store buffer. So there is a buffer which is called the store buffer appropriately, or a write buffer. So all these stores will then go into the store buffer, and then at some later point in time, the contents of the store buffer will get drained to main memory. But your future operations are not getting delayed, right? So that is the key optimization that a TSO memory model allows. And that is what Intel actually uses on your current processors. So your current systems actually have a store buffer or a write buffer, and it allows store load reordering. Fine. Now you might say that, well, there might be situations where you might not want a stored load reordering to happen, right? Because the hardware doesn't know, the hardware will reorder possibly everything. But there might be situations where we don't want to perform a reordering, like say using a synchronization operation or something like that. So how could you do it? So there are some mechanisms that the architecture provides you to help with this. These are called fence operations. So you can insert a fence operation between this store and this load, a fence operation, which will prevent any reordering of these two. So depending on, this fence operation itself is a very huge topic. So depending on what type of reorderings you are talking about, load, store, load, store, there can be different types of fence operations. The bottom line is, fence operations are expensive, because when you insert a fence operation, it is kind of preventing any reordering. So it's kind of hurting your optimizations. It's kind of, it's a kind of a barrier in some sense, right? So everything that is there before has to be flushed out, and only then will instructions after the fence can execute, right? Yes. Why is a load store reorder not allowed? The point is that it is more complicated to implement, and then, as we said, loads are more performance sensitive, stores are not as performance sensitive. So therefore, you don't want to overly complicate your implementation or your architectures, for optimizing something that is not the common case, right? So these are the kind of fence operations that you can have. For example, if you don't want to, reorder a load, you could have a fence operation, so that then the load will always come before the fence. Similarly, other cases, right? But for TSO, these are already not allowed. A load is not allowed to reorder, go down. Load can only go up. Therefore, these are not exactly required. Only these two are required. Basically, a store and a load. So a store comes before a fence. You can add a fence. Then the store will not get reordered. And if you have a fence and then a load, then the load will not be reordered before the fence, right? So now say I have this simple example. The font might be a bit small. So the question is this. So suppose I have a store over here where I store a new to X, right? I load X into R1 and I load Y to R2. Okay? So R1, R2 are registers. And here I am storing new to Y. I am loading Y to R3. I am loading X to R4. The notation is that X and Y are shared memory locations. R1, R2 are like local variables or registers, right? Initially, X and Y are 0, and we are assuming that R2 is 0 and R4 is 0. The question is, Can R1 or R3 be set to 0? Can R1 or R3 be set to 0 in TSO? Okay, so let us look at this case. So the point is, so this is one possible outcome, right? So I have program order for C1, I have program order for C2, right? In SC, program order has to be respected. So these are the program orders, and this middle line is kind of the global interleaving, right? We are calling it memory order over here. So what can happen is, this S1 can get reordered with this L1 and L2, right? These are store and loads. So therefore, this line is showing that, this arrow is showing that in this global ordering, these can get reordered. Remember, store load reordering is allowed in TSO. Similarly, over here, store can get reordered to these loads, right? That is allowed. The only point that you need to be careful about is this guy is writing to X, this guy is also reading from X. So at least you need to be correct in terms of your dependence in program order. So just because your store got reordered does not mean that X can read any, this read of X can return you any arbitrary values. This is also called bypassing. So although this store is going into the store buffer, but what this read will do is, basically then what TSO has to do is, whenever you read something, you need to check whether the value is in the store buffer. If the value is in the store buffer, then read it from there. Otherwise, go to cache and then go through down the memory hierarchy. So now you basically have another level of indirection. You have to go into the store, look into the store buffer first. So that is how this X gets the correct value. Because when you have a read of X, it goes and looks into the store buffer, sees new is there, and then gets it from there, right? So partial store order, we'll go over these slides a bit quickly because otherwise you will not have a lot of time for hands-on. So partial store order is very similar to TSO. By the name, what you see is, it allows store load reordering and it also allows store reordering, right? SC does not allow anything. TSO allows store load reordering. PSO allows both store load and store. Simple. So PSO memory models, these are memory models, those are very popular in the early 90s. PSO, weak ordering, but nowadays these are not very popular. Nowadays only TSO is kind of popular, and then ARM has its own memory model, Alpha. Because this complicates a lot of things. It complicates reasoning about concurrent programs, multi-threaded programs. However, we'll now look at another example. So here I perform two stores, S1, S2, data 1 new and new to data 2, right? Simple. Then I have a flag and then I read from this two. So basically I have a producer thread or a producer core writing some data, setting a flag, then I'm waiting till the flag is not set, and then I'm reading the data. Simple. In SC, nothing would get reordered, remember? In TSO, store doesn't get reordered. Only store load gets reordered. Now the point is, think of it as this way. What this core C2 needs to see is that if it sees flag as set, it just needs to see the correct value for S1 and S2. Do you agree with me? For C2, if it sees flag as set, your intention is that it just needs to see new for data 1 and data 2 as well. That is the semantics. For C2, it does not matter in what order data 1 and data 2 were executed. If I have two critical sections and they synchronize on the same log variable, I want to see whatever was written over here. This one wants to see whatever was written over here. This thread or code does not bother in what order they were executed, as long as you see the final result, right? So this opens up more opportunities for reordering and more opportunities for optimizations. So TSO does not allow that. TSO will not allow you to reorder this too. But maybe because of some situation, reordering S1 and S2 might give you better performance. You see the point? Because now you are this kind of a handshake, right? You are trying to write some data, produce some data, and then give it off. Now, how this data, in what order is it produced, does not matter to the second consumer thread or the consumer core, right? So that allows you for more optimizations. So this is also called a relaxed consistency memory model. So everything is relaxed. In relaxed consistency memory model, you are free to reorder anything. Store load, load store, whatever, you name it. Right? In relaxed consistency memory model, that's kind of the other extreme to SC. You are free to reorder anything, right? The only important thing is that, well, you have to have a correct handoff between these two guys. Yes. No. Like your job is to ensure that flag is set after all this data is set. So the point is, if we are allowed to reorder everything, how do we ensure correctness? Right? That is the obvious question. If we are allowed to reorder everything, how do we ensure correctness? Well, your logic should be that flag should not be set as long as all the other data has been set, has been initialized. Once all the data has been initialized, only then you set flag to true. And similarly over here, within this logic, your logic should be that I will not read any data unless I see flag to be true. Right? This kind of the handshake between these two, the contract. As long as this is satisfied, you are good. Do you agree? Any questions? Yes? Right, so how can we deal with that? We said there is a mechanism, right? What was the mechanism? Fence. So in cases like this, you have to introduce a fence instruction. So what can I do is, I can introduce a store fence over here. I can introduce a store fence over here. That means nothing before me, the store fence, will get executed after. So that means this flag is set is always happening after all the data has been initialized. You see the point? And then over here, you can have a load fence. That means no load that is after me will be reordered, so that all these loads will see the latest information. Right? So relaxed consistency memory model is very fine. It's nice. It provides you a lot of optimizations, but it is one of the most difficult to program for. Because now it is up to the programmer to ensure this correctness. Now you have to think at a very low level. Do I need fences? Do I not need fences? And all this stuff, right? So this is exactly what we were discussing, so I'll skip this slide. Relaxed consistency memory model actually gives you a lot more other optimization opportunities as we were discussing. Some of them are that you can have now a non-FIFO coalescing write buffer. That means from your store buffer also you can actually, emit or commit stores in a non-FIFO manner. So that means store and store get reordered. Then you can support non-blocking reads and a lot of other things. You can now have a simpler support for speculation because anything can get reordered, right? So what are the desirable properties of a memory model? We have looked at a few: sequential consistency, TSO, PSO. We did not discuss weak ordering. We discussed relaxed consistency memory model. The desirable properties are that you want to have a memory model that allows you to have good performance. That means it allows you to perform a lot of optimizations to have good performance. You want a memory model that is easy to program. Relaxed consistency gives you good performance, but it is difficult to program. You see, these are trade-offs, right? This is where the challenge comes. This is a continuum. So there are trade-offs that you have to balance. And then there is also the issue of portability. How can I have a memory model that does not break everything, right? So what OpenMP, and this is now where you come to OpenMP, right? After all this initial discussion, OpenMP actually supports a relaxed consistency shared memory model, right? So you see the challenge? OpenMP supports a relaxed consistency shared memory model. That means if you have multiple threads of execution, then you need to be careful about how the data becomes visible from each thread to the other thread, right? So let us look at this. So it supports a relaxed consistency memory model. So threads can maintain a temporary view of memory that may not be consistent with other threads, right? In relaxed memory consistency model, you can have perform all reorderings are allowed. So threads temporary view of data may not be consistent with what other threads have. That means I can have A equal to 20 over here. This guy may have for a temporary period, it might see A as a 10, right? A different thread can see A as 10. So you have to be careful about these scenarios. Newer specifications said that newer specifications of OpenMP are trying to, make this kind of transparent to end users, to application programmers. So we don't really need to reason about all this a lot, but it's good to know. The operation that enforces consistency is called a flush operation in OpenMP, flush operation. So we'll see here. So hash pragma OMP flush, and then you have a list. List could be a list of variables. So what this tells you is that it identifies the point in the program, right? It identifies a point in the program where a thread is guaranteed to see a consistent view of memory. That means whatever modifications you did, say I have over here hash pragma OMP flush and A comma B, where A and B are variables. Hash pragma OMP flush A comma B. So what this means is at this point, A and B will, the values of A and B that I have will be flushed to main memory, right? And then other threads will have a consistent view of those variables A and B. Flush forces data to be updated in memory so that other threads see the most recent value, right? And in the absence of a list, that means this is optional if you don't provide it, all shared objects are synchronized. You don't need to synchronize private objects, obviously, right? If you have, if you have a parallel region and you have a private variable, there's no need to synchronize it. You just need to bother about synchronizing shared variables. Yes? This is similar to volatile in Java, yes. Not volatile in C++, because that does not ensure it happens before properties. So if the list contains a pointer, then the pointer is flushed, not the address that is dereferenced by the pointer. So it is recommended not to use flushes. You know, as I said, current OpenMP specifications have these implicit flush points at many of these constructs, like you have implicit barriers. So now flushes are implicit at many places. So ideally you should not reason about, or you should not need to reason about flushes, except in cases where you want to implement log variables, say yourself, like spin locks. In fact, I was discussing with someone about this. So those are cases where you are writing low-level libraries, right? You are writing low-level libraries, you might need to reason about flushes, synchronization libraries. The other thing is that flushes are expensive because they involve having fence operations. Remember I talked about fence operations? That means nothing will get reordered. So flushes imply visibility. So they have a, like semantically, they include a fence operation. So that means that kind of impacts performance because fences are expensive. Okay, so the semantics of flush is this. A flush is a sequence at which a thread is guaranteed to see a consistent view of memory. Fine, this is something that we understand. All previous reads and writes by this thread have completed. So when I have a flush, the guarantee I get is similar to a fence. When I have a flush, all previous reads and writes by this thread are now visible to other threads. Make sense? And no subsequent reads and writes by this have occurred. A flush operation is analogous to a fence in other shared memory APIs. Okay, let's move on. So relaxed memory model allows flexibility to OpenMP implementations. So now you think of yourself as an OpenMP implementer, not like an application developer. So relaxed consistency memory model means that once you have A equal to 1 and you have a hash pragma OMP flush A, right? Because this is relaxed consistency memory model, that means as an implementer, you don't need to ensure that A equal to 1 has to be visible immediately. You see the point? Think of yourself as a developer for OpenMP, one who is implementing support for OpenMP runtime, right? So if you see a store to A, because you know OpenMP provides you relaxed memory model, you are not bound to immediately make A visible to other threads. Whether you choose to do so or not is up to you, but you have that flexibility. You are not bound or you are not contracted by the fact that, well, I have to immediately make the store of A visible to other threads. But you have to if you see a flush operation. If you see a flush operation, that is where you need to ensure that the value of A is visible to everyone, right? Yes. So there are certain implicit flush points. So those are like, it is one of them, like an implicit barrier. So a flush operation is implied by many OpenMP synchronization points, right? So for example, if you have an entry exit of a parallel region, a critical section, ordered regions, a flush is automatically implied. Because if you want to have a parallel region, you want to see whatever has happened before that. If you have a critical section, you want to see what is the latest value, right? So you want a flush. You want to read whatever is the latest value, otherwise you will read wrong data. Similarly, there are other points where this is important. So again, as I told you, ideally you will not be expected to make use of flushes unless you are like really into low level or efficient OpenMP programming. So in order to ensure visibility of data, this is what you need to do, right? So I have thread 1, I am writing some data, I have to make sure that thread 1's data or writes are visible to thread 2. So what you need to do is something like this. Thread A will write to the variable, then thread A will execute a flush operation, right? Thread B will execute a flush operation and then it will read from the variable. This will ensure that the value that is written by thread A is seen by thread B. So this is another example. So say I have A, B and C over here, right, stores. I have a hash pragma OMP flush. I have a hash pragma OMP flush A and B. The first one is C. And then I have all these reads of A, B and C, right? So this is what is going to happen. So 1 and 2 may not be moved after 5. Are you okay with this? 1 and 2 may not be moved after a 5, after line 5. That means they cannot be reordered beyond, they cannot be pushed down after line 5. Because line 5 is a flush on A and B. That means I am inserting fence statements on A and B. So the store of A and B cannot be reordered after this fence instruction, right? Similarly, 3 cannot be reordered after 4, right? If I did not provide this C, A and B, then none of these can be reordered. Then it's like a flush on all shared objects, all shared variables. 6 may not be moved before 5 because this is a flush. So therefore, you cannot bring anything up before this flush or fence operation, right? Simple. This I think is an example of OpenMP flush. So what we are trying to do over here is we are trying to implement a spin lock. We are trying to implement a spin lock, right? So what we'll do is over here. So we have a hash pragma OMP parallel, right? So I have a producer. So the producer is producing some data over here. Simple. And then the producer is setting a flag to 1. Now the point is you have a consumer. The consumer is reading data after it sees the flag is set to 1. This is again very common paradigm that we have. But you need to be careful in cases like this. Because I am not actually using OpenMP synchronization constructs like critical or atomic or whatever, right? So you need to ensure, you need to see whether hash pragma OMP section already includes the implicit flush. If it does, then that is fine. If it does not, then you will need to introduce flushes yourself for correctness. You see the point? If a section and all has an implicit flush, then you are good. If it doesn't, then you will need to ensure that this flag is flushed so that the other thread can see flag. So one way to do it is that, well, you produce data and then you have a hash pragma OMP flush, right? Then you write flag 1 and then you flush flag, one possible solution, and then you flush flag, and then in the other thread you flush flag and then read flag and then read data, then consume data. So you see the trouble over here? Yes, this is a slightly involved example. Any questions? We are adding a flag, we are adding a flush in the consumer because we want to ensure that whatever we want to see the latest value of the flag that is being written by the producer. Right. Should it not only be reordered, it should also read the latest value that is there in memory. Right. So therefore, we are having this right, and then we say hash pragma OMP flush flag. That means ensure that this value of flag is now visible in main memory. And then from the consumer thread, you emit a flush, then you read flag. Hopefully now you are guaranteed to see flag is 1, and then you can go ahead and consume the data. This can be achieved by volatile variables in Java, right? Some of you said or talked about volatile variables. In Java, you could do this. You could initialize an object, set a volatile variable to true, read from the volatile variable, and then consume that data. Because volatile has similar semantics in Java. It introduces or it ensures happens before relation. So these are the last couple of slides. We're close to the end. So what this allows you is that if you are writing an OpenMP optimizing compiler, you can reorder operations freely inside a parallel region for reasons of performance, right? You are free to reorder operations within a parallel region. However, parallel region, at the end of a parallel region will contain an implicit flush and other things. So there are a few other constraints that you need to keep in mind. For example, you cannot move operations out of a parallel region or around synchronization operations, because that means you are kind of reordering across fences. So these are some limitations that you have to keep in mind if you are a developer of a optimizing compiler for OpenMP. It provides you some features, but there are also some constraints that needs to be respected. And I think that is the end. Yes. So any questions? Yes.
The question is related to application.
Okay.
OpenMP is in C++. Most of the code which we write is in Python.
Okay.
How do we apply
So the question is that how is open? So let me understand your question. Are you asking whether OpenMP is applicable to Python, or is there a way to? One thing that you could do is you can embed C code or C++ code in Python, and that code could use OpenMP.
Can we use PyML?
PyML.
Yeah, something similar to OpenMP.
I have no idea about it, unfortunately. Sorry. So if you want to use OpenMP within Python, obviously you could embed C code or C++ code, right?
Non-FIFO coercing of private body. So could you explain more?
What is that? Okay, fine. Good question. I didn't want to, I thought that would take some time. So we talked about a stored buffer or a write buffer, right? So once you are done with the operation, you put it into the store buffer, and then it will later get drained out into memory. So say I have 3 stores. Store equal to A0, right? Some address. Store equal to B0. Store A0, store B0, store A1. Try and visualize it. Store A0, store B0, store A1. 3 addresses, right? And these are now in the store buffer. Fine? There could be a scenario like this. Now assume that A0 and A1 are kind of adjacent addresses. B0 is a far off, right? If you have a FIFO write buffer, first in first out write buffer, like TSO does not allow reordering of stores, right? So TSO requires a first in first out write buffer. That means first of all A0 will be drained out, then B0 will be drained out, then A1 will be drained out. So it's like 3 memory transactions. Agreed? Because stores are not reordered in TSO, right? In relaxed consistency, stores can get reordered. So I have store of A0, B0, A1. Can you think of an optimization that is applicable if you have a non-FIFO coalesced write buffer? Do you see what I'm trying to hint at? What is it? So the thing is that if I have a non-FIFO coalesced write buffer, since A0 and A1 are together, but A1 comes later, but as an optimization, I can club them together in the same memory transaction, conceptually, and I can drain it out, right? Because they are together. What this means is, effectively, B0 and A1 are getting reordered. B0 and A1 are getting reordered, so that is a store-store reordering, which is not allowed in TSO. Therefore, TSO requires a FIFO write buffer or store buffer, but relaxed consistency allows you to have a non-FIFO coalesced write buffer. Make sense? Just a minute. Do I put up the questions for them to try it out and then maybe continue answering? So let us do this. So we have a few simple problems for you to practice, right? So I'll put them up because we are anyway a bit behind schedule. I'll put them up. So start trying, and meanwhile I can continue taking questions from you guys. So can we hold on for some time? So please go to this web page. So I think you guys have access to this cluster, right, to this infrastructure. So log into your directories. What I would suggest is log into your directories, right, and then try and wget these files. So these are some simple problems that we have. So we have 4 problems. So you can view it over here. This is the URL, cac.iitk.ac.in, users, my name, ACM Winter School HPC 19, ACM WS HPC 19, and hopefully that will give you this. So we have a few problems that you can try out, pretty simple, based on what ideas we have mostly learned yesterday and today. Try them out. And I have also provided a few sample files that you can already use to get started, so that you don't need to start everything from scratch, like int main void, hash include, iostream and stuff. So you can download them to that directory that you are using for on the CDAC infrastructure, and then hopefully you should be able to compile and run it. I also have compilation instructions over there. Okay. So let us just do one thing. Let all of you try and log into the CDAC infrastructure. Once you are done, then I can tell you what to do. Please try and log into the CDAC infrastructure. Is it done? Yes. So then what you can do is, you can just do wget. So you can copy this URL, copy link address. So from terminal, what you can do is, you can say wget and then the URL that I showed you, right? By this way, you will be able to download the CPV files on those clusters, on those systems, and then hopefully you should be able to compile and execute them. URL here, caciitk.ac.in, users, unfortunately my big name, and then /ACM Winter School ACM WS HPC 19. Is it not working? It's simple, problem 1.cpp, problem 2.cpp. So once you have one, the others you can just reuse the. Yeah, I think that is already connected. If you go to the terminal, it was showing some output, yes.
So here you can.
Okay. So do I need to copy it to some other directory? Student?
Here itself we can create that.
Okay, so let me. Continue. Okay, so as Preeti was saying, we have a directory called advanced-openmp, and there we have this PDF file if you need it, and 4 CPP files, which are basically templates. So in most of those cases, I have given a serial implementation or a reference implementation, and we have asked you to, parallelize it using different ideas in OpenMP, work sharing, tasks, and so please try it out. Let us know if you have any issues. In the meantime, I can take questions.
Vector instructions, how are flags
You mean these concurrency flags?
code Intel has got those vector instructions.
Mm-hmm.
And there was one instruction, jump if less.
Okay.
So it essentially would be checking flag.
Huh.
So in a scalar, you can easily, in scalar, you know that there are 2 operands and 0.
Okay, okay. So you're saying that if you have multiple operands and then say the flag difference, the flag is different for different operands. Is that what you're saying? Okay.
Or maybe I will also hunt for it.
So in GPUs, what happens is, it's like this divergence thing in GPUs. So basically, then you have, I'm not exactly sure how is this implemented in a CPU context. In GPUs, what happens is if you have different, flags sort of thing, then they will take multiple passes over the same instruction with different masks. So in some sense, like, maybe say indices 0, 1 are enabled, rest are disabled. So the first mask could be just 0, 1. So I'm not exactly sure about. No, that is a good question. I hadn't thought of it, but.
And in that slide that you showed about that Intel scale up, in the last one it was like phenomenal. So did they explain
No, so no, that was something that I don't have a lot of insight upon. So it's like just a slide that they have in their, these public presentations. But not a lot is known about the exact benchmark that they have. And if you look at it, this metric also is different. That is some binomial operations. It's not like our regular, like say, cycles or, flops or so. So. Sorry, could you repeat? That is something that Intel has not yet officially agreed. It's more conjecture, but that is fine. Okay.
I cannot reorder the rights that you were mentioning, A0, B1 and A1.
So stores are not reordered with other stores, right?
But Intel is
So out of order execution is the execution. The commits are in order. So there is a difference, right?
commits are in order. But usually I have that if the hardware finds that two addresses are adjacent, the completion buffer, it will go in.
No, that is a optimization that TSO does not allow. It is an optimization that you can use if you had a weaker, like say PSO or a relaxed memory model. So a TSO uses a first in first out store buffer. So the order in which it enters, that is the order in which it will drain, because stores are not allowed to reorder. If you are using a memory model, that is a PSO, where stores can get reordered, or which is relaxed consistency memory model, then you can use much more optimized implementations of a non-FIFO coalesced write buffer, where you can, coalesce adjacent memory locations. So this optimization is not allowed for TSO. Does that answer your question?
What you are saying is the order in which it goes into the write buffer is what is controlled by TSO.
Yes, and the order in which it is drained out also is controlled by TSO.
Oh, it can through instruction it can tell the CPU that what I understand is Intel implements what is called as write merge.
Okay.
So wherein two adjacent, like if it's a part of the same line in the cache, and if they are let's say following each other, then it can merge. So what model is being followed at the upper layer?
So first of all, is write merge applicable to non-adjacent stores?
No.
So if I have adjacent stores, like two stores after the other, that can be merged, and that does not violate TSO. But say if I have A0
In between, if there are some reads you are saying.
or other stores, so will write merge work then? Okay.
No, it's like a what is called as a burst write, that you give one address and you have multiple writes happening because the bus is wider and
Okay.
the data structures are smaller.
Okay.
But essentially they are going into the same cache line.
Then okay.
So that's what is done at I think the hardware level.
Okay.
Reduce the number of cycles.
So
That I think TSO may not mind that, and I'm more concerned whether TSO can dictate that to that hardware part because.
no, TSO is hardware.
Oh, okay.
TSO is hardware. So maybe I was not very clear about this, but you can think of your hardware, your RTL or whatever logic you have, that has to respect TSO. So if you have write merge, if you have whatever.
It's at the architectural level, that's fine.
Huh.
I thought it is like a
No. TSO is at the architecture level. So if I am a developer of a open source architecture that maintains TSO, then I have whatever write merge or whatever other optimizations I do, I have to respect these optimizations. Right.
And one more thing, say for example, so you talk about end-to-end memory model. We always have to do that.
That is important, right? Because, okay, so this is actually a good question. I do not want to touch upon on this. The point is, say I have an application program, right? I'll have a compiler. Then I will have an architecture that will get executed and I have the final executable. Now the point is, say, think of a scenario where, like, say my compiler is relaxed consistency and my hardware is SC. So what do you think will be the final outcome? What is the final memory model of the final executable? No, it will be the relaxed consistency memory model. So you have a program, you have a relaxed consistency compiler, you have a SC hardware, right? The point is the relaxed consistency compiler can already perform all reorderings before the SC actually comes into picture, right? So therefore, end-to-end memory models are kind of important. Think of it the other way. You have a SC compiler and a relaxed memory model hardware. So then the SC compiler is kind of useless because the hardware can do anything, right? So therefore, end-to-end memory models is actually very important. So it's kind of a contract between the programming language environment, the compiler, and what the hardware can do for you. So if I have a very restrictive compiler and I run it on a very, relaxed, aggressive hardware, then I am kind of wasting my opportunities for optimization by using a restrictive compiler. So therefore, it's kind of a, there's a closer relationship between there than thinking of it as separate black boxes. So that is why end-to-end concept is important. So if I have a SC program, SC compiler, the hardware is TSO, then the SC compiler is kind of not doing anything meaningful because the hardware can reorder stores and loads. Programmer needs to know in the sense if you want to write portable code, if you want to write code that will run on different architectures. So then these are concerns that you need to be worried about.
So basically, the compiler writers have to influence the architecture so that
it's kind of both ways. It's kind of both ways. In the 90s, all this memory model research in the 90s were spurred by hardware developers or architects like TSO, PSO. They come first. So the hardware memory models came first because in the 90s and all, they proposed an optimization, like they proposed a store buffer optimization, and then they thought as an afterthought as to like what kind of reorderings is this allowing, right? But then once this multi-core era trend came in, then this sort of complicated reasoning about correctness and programs. And then the compiler developers caught up, well, we need to be, because of this end-to-end business, we need to also have a contract or we need to also have a visibility to, to have an end-to-end model. So the compiler developers were kind of lagging compared to the architects. So Java, in fact, is one of the first programming languages which had a well-defined memory model because threading was kind of first-class citizen in Java, right? And now C, C++ have all caught up. In fact, languages like Ada and all also, I think, have a very well-defined memory model. So how it influences is like, as a compiler developer, you have to see what is the target. So if your target is a alpha or a DEC machine, then you can potentially perform more optimizations, more reorderings than if the target was like say Intel machine or a SC machine.
And I mean possibly in this case the EPIC architecture that IIT proposed would have been a better one because the aspects of hardware are exposed to the compiler and they have a more synergy than x86 architecture.
Okay, that is possible. I don't have a lot of insight into that.